Welcome to the Waterloo Willington Children's Groundwater Festival.
Well, good morning, everybody, and a fine welcome to you all. And thank you for joining us for our final day of the Waterloo Wellington Children's Groundwater Festival. Now, even though we are together from a distance, we are so glad you're with us today. For the next 60 minutes, we're going to have lots of information coming at you. And today's event is actually being recorded. And registered attendees will receive an email with a link in the coming days. But first, I'd like to start today with inviting Michael to share the land acknowledgement. Sir, if you would.
Thanks, Kevin, and good morning. And good morning to all of you. Before we begin, I'd like to acknowledge and recognize that the water and the land that we'll be talking about in Wellington and Waterloo is the traditional home of the Haudenosaunee and Anishinaabe people. For thousands of years before European settlers came, these indigenous groups took care of the water and took care of the land and made sure that all living things had a safe place to live and thrive. Now these groups, the Haudenosaunee and the Anishinaabe people, they're not gone. They're still here, and they hold traditional knowledge that can help us make sure that our environment is safe for years to come. I encourage all of you to ask questions and learn about indigeneity. Working together is always the best way forward. Now, let's begin. Back to you, Kevin.
Thanks so much, Michael. Much appreciated. Now, do you have any questions about water? Because some of our friends had their questions already answered. Let's listen in.
We asked them some water-related questions. If you could sail anywhere, where would you go?
I went to Camp Wabanaki in Honey Harbor in Georgian Bay for 8 years as a child and as an instructor. And our oldest daughter went for 8 years too. So I would tell you that I would love to sail around Honey Harbor and in Georgian Bay again. I love the hard rocks with the green lichen on them. I love the windswept trees. And I love the beauty of the sun glistening on the water.
I could sail anywhere. I would say I'd sail to Narnia. That would be an amazing world to discover.
Where would it be? I guess I would say I would love to sail probably to Australia, the other side of the world. I think that would be a long trip, but quite fun.
What have you learned about water that you didn't know when you were a kid?
I grew up along the shores of the Grand River. And when I was a kid, we would splash in it, swim in it, skip rocks across it, put ropes on trees and swing out and back. And it was a wonderful, glistening playground for us. But as I got older, the Grand River got so polluted with sewage effluent and other things that the fish started to die. And what happened with a concerted effort by residents and by the region of Waterloo is that Grand River came back to its natural, pristine beauty. And now you can swim in the Grand River and you can catch fish in the Grand River. And what I have learned through that experience is what we do can cause a river to be polluted, but we can also work really hard and bring it back to its natural, good, healthy condition. So what we do towards our water makes a huge difference.
I learned that there are lots of lakes and rivers underground, not just above ground, but underground. As a kid, I never knew that.
I would say probably the biggest thing about water is just in general the theme of conservation. So that is a big thing for me. I think when I was a kid, I didn't know there was, that it could be a resource that needed to be protected. I thought it was just turn the tap on, it just comes out like magic, and there's no issue with it. So learning a lot more about why it needs to be protected is something I've learned growing up.
Today, we're talking about water systems. We'll learn about how we manage water and their distribution systems. And if you have a question, make sure you put it in the chat. because we have a team of water experts standing by to answer your questions. And when you're using the chat, remember, it's important that we are respectful and only share questions and comments about water and what you're learning today. And I have friends in the chat room who, if necessary, can remove comments or even put you in a timeout. But, you know, I don't think that's going to be necessary today, is it? Because you fine folks are a respectful lot. Now, we're also using slow mode today. Now, that means information typed into the chat will be delayed just a bit. So please be patient with us as we're answering your questions. Now, you ready to start? Because to start with, we're going to take a tour of the Shand Dam.
I've always been interested in water ever since I was a kid. This particular dam was the first project of the Grand River Commission. And essentially what a dam does is it holds back water and allows us to release it. So when we have too much water, when we have a flood, or in the spring when we have too much water, the dam can hold that water back. We release some of it in a controlled fashion to try to reduce downstream flooding. And then over the summer, when it gets really dry like it's been this summer, we can release water to add additional water to the river. Otherwise, the river would be really dry. The Grand River Conservation Authority really got its start as a result of water problems in Waterloo region, in cities like Cambridge and Kitchener. When the upper portion of the watershed was cleared and converted to agriculture production, a lot of wetlands were drained. It changed the hydrology. And when it changed the hydrology, it started to create floods and droughts. And the water quality got so poor it was making workers sick. That affected industry, it affected the economy. The local Economic Board of Trade in Cambridge and Kitchener-Waterloo region went to the provincial government and requested the provincial government commission a study to look into how floods could be reduced and how water quality could be improved. Following that, the Economic Board of Trade recommended that a watershed authority be commissioned or formed to try to solve some of the flooding and water quality problems. And they created what was called the Grand River Commission. The first project of the Grand River Commission is this dam, Shand Dam. And that's important for water supply, and it's important for helping to dilute treated effluent from the river. Waterloo region has invested a large amount of money in updating the Kitchener-Waterloo sewage treatment plants, and that's improved water quality in the river. The way we see it reflected in the river is not only improved water quality, but a change in species. At one time in downtown Cambridge, people fished carp, now they fish pickerel. That's an incredible change, and the regional tourism around the river has flourished because of the improved water quality. Waterloo region takes about 25% of their water supply from the river and about 75% from groundwater. Our operating procedure for this dam and downstream is basically to maintain a minimum flow through Waterloo region in the summer of 10 cubic meters per second. 1 cubic meter a second is equivalent to 1,000 liters. But people have to realize they serve two purposes. They help reduce flooding and they supply water to the river. And those are competing needs, and our reservoir rule curve helps try to find that balance. So this is electrical equipment that basically provides energy to the gate motors to operate the gates. So on each side of the gate there's large screws, and that's what lifts the gate. So there's a motor up top. It turns gears that basically pull those screws vertically, and that lifts the gate. So these large blocks and this concrete structure down here is what's called the stilling basin. So when water discharges from the dam, it has a lot of energy. So these blocks tend to slow that water down, and there's a deep pool off the end that allows the water to basically roll but not erode. This is our hydro plant, and we'll be taking you down inside that box structure. So this is one of the 48-inch valves, so it's a low-flow pipe with a big valve on it. You can see the valve operator in the back. And we can actuate the valve or open the valve to let water out through this pipe. We're going to be discharging water anyways, so we put a hydro turbine on it to generate some energy, and it generates some revenue for us. That's the generator. So the turbine turns the generator, that generates electricity and delivers it to the grid. At peak, 690 kilowatts, and that would power several hundred homes.
Do you know the Grand River Conservation Authority manages 27 dams? Important infrastructure is needed for managing our water, and this includes the Grand River that drains into Lake Erie, one of the 5 Great Lakes. We're now going to join John Johnson, a geologist with the University of Waterloo, to learn all about the Great Lakes.
So maybe we can start by first telling us which lakes make up the Great Lakes.
There are 5 lakes in the Great Lakes, as shown on this image right here. I've got a few props that this neat shape of Lake Superior, the largest lake, is like this really large container right here. So if we stick this on here, we would put it way up north at the head of the system. And then we would have 2 other lakes, Lake Michigan and Lake Huron. They go north-south, or Huron's kind of like a hand type shape. And they go below Lake Superior, right here and here. And then we have 2 other lakes. We have Lake Erie and Lake Ontario, which kind of go east-west and are elongated in that way. And they go here and here. So the Great Lakes consist of 5 big lakes: Superior, Huron, Michigan, Erie, and Ontario.
Oh, great. Yeah, so now we know which of the lakes make up the 5 Great Lakes. When we look at the Great Lakes, which way does the water flow?
Great question. We have given you a handout to actually look at and follow along with us on the direction of flow of the Great Lakes. So if you pull out your handout, we have some lakes listed in the bottom, and we have some blank areas in the top. And if you follow along in Lake Superior way up north, in this blank right here, if you write Lake Superior, water begins here and flows down to Lake Huron right here. And so you can add a label right here, Lake Huron. But Lake Huron and Michigan are the same level. There's a wide enough space between these lakes that water can go back and forth, and it's one lake level. And so this long and skinny lake is Lake Michigan. And then it can flow down through a river to Lake Erie here. And so if you fill this out as Lake Erie, and then over Niagara Falls, through the Niagara River down to Lake Ontario right here, and then down the St. Lawrence River all the way to the Gulf of St. Lawrence, and then to the Atlantic Ocean. So it goes all the way from Lake Superior up high down to the Atlantic Ocean through many stair steps.
Well, that's a long journey for a water drop. So we saw sort of the journey of the water, but how does water make it from Lake Superior to the Atlantic Ocean?
Oh, great question. We created another handout for you to follow along in this profile or elevation or stair steps from really high elevation to low elevation. So we're talking Lake Superior is 183 meters above the Atlantic Ocean, which is a relative zero down here. And so if you're up high in Lake Superior, you go through a lock that helps hold up the water or release it and go through the St. Mary's River to Lake Huron. And Lake Huron and Michigan are drawn as one here. Lake Michigan a little bit deeper and Huron a little shallower, but they're a similar level at 176 meters. So the water level from Superior to Huron and Michigan is 7 meters. In the St. Mary's River, it cascades down to 176 meters. And then the water flows into Lake Erie. And the difference in elevation between Lake Huron and Lake Erie is only 3 meters down the St. Clair and Detroit River. And then from Lake Erie to Lake Ontario, it's a big fall. Across the Niagara Falls, through the Niagara River, it goes down about 100 meters, down to 76 meters above sea level. And then it takes other steps through a number of locks down to the Atlantic Ocean. So we go from 183 meters all the way down in stair steps, some of which we help to regulate and hold up the water or release the water.
Wow, that's a big journey and a big drop from the top of Lake Superior to the Atlantic Ocean. So when we look at the Great Lakes, which one do we in our watershed, in the Grand River watershed, which one do we have the most impact on?
Right. Many people think about this lake right here, this small shallow lake called Lake Erie, which has been in the news quite a bit because of the algae blooms or the green looking tinge of the lake, which sometimes impacts life and fish and is not good. And that is washed in from a lot of the agricultural practices surrounding the lake and in the watershed. So that's pretty important and impacted quite a bit. But let me turn your attention to Lake Ontario. We have a lot of big cities in Canada and the US beside this lake. And we also have at the end of the system a whole bunch of locks holding Lake Ontario up, so that water is sometimes released and sometimes held in the lake. And so we've created a level lake, which isn't always good for the wetlands to be healthy. They need that natural oscillation. So we regulate those locks to allow those natural oscillations to keep all the wetlands around Lake Ontario healthy.
So thank you so much, John, for your time and for sharing your knowledge with us today.
You are welcome.
The Great Lakes holds about 20% of the Earth's fresh water, providing drinking water for over 40 million people. Here, we rely on groundwater. And Pete is going to talk to us about how we use wells to collect groundwater, and then it's over to Levi to learn more about how groundwater moves underground.
Hi, I'm Pete, and I'm here to talk to you about wells. So a well is a hole that's made in the ground for the purposes of locating groundwater, or to test the materials, the gravel or the rock, that the groundwater comes from. So the earth acts like a sponge. It rains and it snows on that sponge year after year. And the water, the rainwater or the melting snow, soaks into the ground. And eventually, at some point beneath the ground, all the spaces between the soil particles are filled with water. When they're shallow and it's close to the ground surface, they're filled with air. But when you get to a depth, certain depth, they're filled with water. And at that point in time, we've encountered groundwater. It's like when you're at the beach. If you dig a hole beside the shoreline and you start to dig, the hole is empty, has no water in it. But if you dig down deeper, then water comes into it. So the shallow soil, all those sand particles are filled, the spaces are filled with air, and beneath that, they're filled with water. And a monitoring well is a smaller diameter or smaller width. It's only about 15 millimeters or a centimeter and a half or 2 centimeters in diameter, but we can drill these to all sorts of different depths. The purpose of these wells are to let us measure water levels and collect water samples from different depths. So this next video is a video of Jeremy showing us how we measure water levels in our monitoring wells.
So my name is Jeremy, and today I'm at a quarry. I'm here to conduct some groundwater monitoring, which involves taking water levels and groundwater samples. So beside me here you can see a monitoring well. Now this well is just a white PVC pipe in the ground with a cap on top so that nothing can fall in. This well was constructed before the well regulations were put into place, and so it doesn't have a protective casing around it. Wells that you would see today, they would need to have a protective casing. So this well is drilled to a shallow depth, and then beside me we have a well that's drilled to a deeper depth. And what this allows is for us to understand how groundwater moves in this area. So what we're going to do today is take a water level out of this well. So taking a water level is a fairly simple task. We'll start by taking off this J-plug that's protecting the well, and then we're going to take this water level tape, and all we have to do is insert this probe down the well. When this probe reaches the water, it'll send a signal up the tape and it will beep. So let's do that. So you can see it measures to 88 centimeters on the tape, and now we need to bring the tape up to find the meter mark so we can get an exact value for our water level. So you can see there 3 meters and 88 centimeters, 3.88 meters is our water level in this particular well, and that is measured below the top of the PVC pipe. So always remember to seal the well back up to maintain its integrity, and then record your data in your field book.
So we're here at my farm where I live outside the city, and I have a well. And you can see the well, it has a lid, it has a black steel casing. In this case, this well is about 25 meters deep, and you can see the lid, it's secure so nothing can fall into it. So drilled wells tend to give us better water quality because they're deeper, and the water that we're taking is further away from the ground surface, so we aren't going to typically have some shallow contamination that affects them. So they supply all the water that we need. We have a pump in the bottom of the well that pumps water into the house. Some of our communities rely on drilled wells, like the city of Guelph and the region of Waterloo, and in this case these wells are a larger diameter and deeper than my well, and they produce much higher quantities of water. So while my well might provide 20 liters a minute, these municipal wells can provide 2,000 liters per minute. So groundwater is something we have to protect. Wells are one of the ways that we take groundwater out of the ground, but they're something that we have to maintain and keep safe so that our water quality is good for us to drink and that we don't take too much water out of the ground. Thanks for joining me.
Now that we all know what groundwater is and how it moves down into the ground, let's explore how it moves through different earth materials. Years ago, all of Waterloo was buried underneath a huge glacier that was hundreds or even thousands of meters deep. It was roughly equivalent to 4 CN towers tall. That is a lot of ice. Now, these glaciers were dirty. They were full of sand, gravel, and other stuff. And about 12,000 years ago, that ice melted, and as it did, the stuff trapped in the ice, remember the sand, the gravel, and the clay, was all sorted into layers, hundreds of meters thick. This model is very similar to what is below our feet in Waterloo region. So, here are some of the wells. Here's the river. This would be like the Grand River. Here's the lake. This might be like the lake in Victoria Park. And this is the stuff underground. These are artificial structures that we put there. Now there are several layers in this model. At the surface, this green stuff is meant to represent vegetation. So that would be the plants and the grass, the trees. And below that layer, there's some coarse gravel, and then some fine sand, and then some coarse sand, and wedged in there are some clay layers. If we were to follow well 1 all the way down, you'd notice that it runs into something, and this is meant to represent the bedrock. In Waterloo Region, the bedrock is dolostone and limestone, and it's highly fractured, and these lines represent those fractures. In some places, like Lower Gorge, the bedrock is near the surface, and you might see this if you went for a walk in that area. But in other places, it is hundreds of meters underground. This is a core of the bedrock from Waterloo, and you can see here that there are fractures, and in these fractures, this is where the water is held and where it would flow. This is what makes it an aquifer. Of course, sand and gravel also hold water and allow it to flow, so these are also aquifers. Some material, like clay, is exceptionally slow at letting water flow through it, and so we would call that an aquitard. It's slowing the flow of water. All right, so now we get to do the fun part. We're going to show you how water flows through this system, and to do that we're going to use dye. I'm going to invite my assistant over, and she's going to actually apply the dye. So everybody, this is Alba, and we're going to give her the syringe. Here's our blue dye, and you're actually going to squeeze it and suck some blue dye in, and she's going to add a little bit to each one of the wells, these first ones here. Go for it. Yeah. The height of the water underground is what we call the water table. So in here, you can see, because Alba's added blue dye to all these different wells, we can now see where the water table is. I'm going to use this red pen, and I'm going to connect the river to the depth of the well, the water in the wells, to the lake, and we'll see visually where the water table exists. And what you notice is that it's not a flat line, that it follows topography to some extent. The depth of water underground changes depending on where you are. That's pretty important if you're a farmer or if you live in the country and you need to get your water from underground. You want to know how deep the water is, so you know how deep you're going to drill. The height of the water underground also changes with time and with precipitation. And at the top here we've got a pump that's pushing water through our system, and it's over here on the right in our area of recharge. This is where the water, when it's raining or when the snow melts, water enters the ground. So right now it's raining. If I move the pump over, it stopped raining. And you can see, you should see in a second, the blue is going to start dropping in each one of these wells. So as the rain decreases, the amount of water entering the system decreases, and the amount of water underground decreases. So here you can see it's well below that red line. And it's going to keep dropping the longer we leave it off. Of course, it'll eventually rain again, so let's bring this back. And wow, look how fast that is. There's a good rain event, a nice thunderstorm. The ground is going to quickly recharge. One of the other things that I thought we should explore with this model is how the water enters the system over here, but it exits over here in the river. So this water is flowing from one side to the other. Now, we've got several different layers, several different aquifers. The water is going to flow through them at different speeds because of the pore spaces, because of the size of the material. So the gravel, it's a pretty big material, and that means the spaces between those materials is quite large as well. So in theory, if the spaces are larger, the water is going to flow faster through that. Up here in the sand layer, the particles are smaller, so there's smaller spaces between the particles. That means water can't flow quite as fast through it. So if I was to guess which of these 4 layers the water is going to flow the fastest, I would guess that the fractured bedrock is going to be the fastest because the pore spaces are the largest. And this fine sand layer at the top is going to be the slowest because the particles are so much smaller. There are other layers like this clay layer. They're going to act in a different way, but we'll come back to that in a minute. So I'm going to add a little bit more dye, and then we're going to flush it. We're going to see which one flows the fastest. Now remember, our theory is that the water's going to flow really fast in this one. And look, follow Alba's finger. It's already flowed almost all the way to the other side. Number 2, it's only about halfway. And in number 1, in this one, it's only moved a little bit, maybe 2 centimeters. So the size of the material is really important for how quickly the water flows. And fractured bedrock is the fastest, fine sand is the slowest, and then these cobble and gravel and coarse sand, they're in the middle. Well, I hope you enjoyed this amazing aquifer and learned about how water flows through different materials. Bye, everyone.
In Waterloo Region, some of the drinking water starts at the Grand River. Now, come with me on a tour of the Mannheim Water Treatment Plant to find out what's involved in treating water from the Grand River. And then we'll learn why water towers are an important part of the distribution system. And finally, we'll also find out about the many ways we test water.
Waterloo Region depends on the Grand River for 20 to 25% of its drinking water. Treating water from the Grand River takes more work and energy than treating groundwater. Water in a river is exposed to human and animal activity, plus the effects of weather. The journey begins at the Grand River in the Hidden Valley area near the Highway 8 bridge between Kitchener and Cambridge. A weir redirects the water into a low lift. Inside this building are screens that keep out large debris and branches. The water then moves through a pipe to a large reservoir with 4 storage tanks. The reservoir can hold 142 million liters of water, enough to fill 2,800 backyard swimming pools. The reservoir serves 2 purposes. First, it gives time for sand and dirt to settle out of the water. The reservoir also builds in a safety delay. If the region of Waterloo learns of contamination in the Grand River, say a chemical spill from an accident, the reservoir provides several days of water while the river is cleaned up. After the water leaves the reservoir, a pump helps to move it 10 kilometers uphill through a large underground pipe to the water treatment plant in Mannheim. The treatment plant is on one of the highest elevation points in Waterloo Region. Being up so high allows the use of gravity to help water flow downhill through the treatment plant. Using less energy reduces costs and greenhouse gases associated with climate change. The treatment plant can treat up to 840 liters of water every second, but normally it produces between 400 and 600 liters per second, about 40 to 50 million liters of water every day. The water first enters one of 2 raw water tanks before entering the plant to begin the treatment process. Each tank can supply the plant with about 60 minutes of water. Inside the plant, the water completes a multi-step treatment process. Step 1 combines 2 steps, coagulation and flocculation. A polymer is added to the water that helps tiny particles such as sand or algae stick together and form large clumps called flocks. Look closely and you might be able to see the spinning wheel slowly moving at the bottom of the tank. The spinning wheel helps to mix the polymer with the water. Step 2 is sedimentation. Water flows through the plate settler from the bottom up. The plate provides a surface area for the flocks or clumps of dirt to fall onto and slide down to the bottom of the tank. The flocks are then pumped outside to be dried and treated. Step 3 is ozonation. Ozone gas disinfects the water by deactivating bacteria and viruses, as well as improving the taste, smell, and color of the water. Ozone gas is produced at the treatment plant from liquid oxygen. After the ozone gas has done its job in the water, the ozone gas molecules change back to normal oxygen. Step 4 is filtration. The water moves through layers of sand and activated carbon to remove any remaining silt, viruses, bacteria, or other impurities. Filtration also helps to remove cloudiness from the water and make it clear. Important for the next step. Step 5 is disinfection using ultraviolet radiation. The water flows through a large pipe with special lamps that shine ultraviolet or UV rays through the clear water. This instantly deactivates all sorts of pathogens such as viruses, bacteria, and other microorganisms that can make people sick. Step 6 is disinfection using chlorination. Small amounts of chlorine added to the water disinfects it for viruses and bacteria. Chlorine doesn't kill every type of microorganism, which is why UV radiation is included as the previous step. And unlike UV radiation, a bit of residual chlorine stays in the water to keep it clean as it travels through underground pipes to your home. Each step is carefully monitored 24 hours a day, 7 days a week from a high-tech control room. Water operators can track what is happening throughout the plant and start or stop the system. The plant has 2 separate treatment processes. If any process is shut down, the other side of the plant can keep operating. Testing the water is an important part of the treatment process to make sure the water is clean and safe to drink. The water is tested before, during, and after treatment. Ontario has a Safe Drinking Water Act, which sets the legal safety standards for municipalities. These rules are strict and require regular testing of drinking water. It takes about 8 hours from the time the water enters the treatment plant until it leaves as clean drinking water. After the water leaves the Mannheim Water Treatment Plant, it is mixed with groundwater from nearby wells before entering the distribution system that delivers water to homes in Waterloo Region.
Hello everybody. So in this presentation we will be talking about water towers and the water distribution system. Before discussing the water distribution system, it's important to understand where the water you drink and bathe comes from. So your drinking water in Guelph is 100% groundwater, and in the region of Waterloo, 80% is groundwater and 20% is from the Grand River. Groundwater is the rain and melted snow that soaks into the ground. Groundwater fills in the tiny spaces between sand grains, gravel, or rock that make up layers in the aquifer. Groundwater wells throughout the regions collect the groundwater. In the region of Waterloo, over 120 wells supply 120 million liters of drinking water each day. A pump is used to extract the water, which is then tested and treated before it enters our pipe network. Our pipe system plays a great role within the distribution system. Another main component of the distribution system are our water towers. Our water towers pressurize water. So by elevating the water, they ensure that the water is being pressured, which is driven by gravity, and this forces the water down and throughout the system. Pressure is a way of measuring how much force is acting over an area. Fluids can exert pressure too. So imagine being submerged in water. The water above you would be pushing down on you because of the force of gravity, and would therefore be exerting pressure on you. If you go deeper, there will be more water above you, and the weight and pressure from the water would therefore be greater. So the height of the water tower is what provides the pressure for the water within it and in the distribution system. As discussed on the previous slide, a water tower is a large elevated tank of water. To maintain the required pressure in the distribution system, the water tower must be tall enough to provide the level of pressure to water users in the area. Here is a video of us interviewing a water tower supervisor.
Hello, what's your name? My name is Martin. Martin? Yep. Hey Martin, so what do you do here at the water tower?
I work with the Regional Water Department. Okay. My job here is to make sure that the water's safe, so I'm in compliance. Okay. So my job is to make sure that what we're doing is in compliance with the region and the ministry's regulations. Yes. So make sure water's safe, no bacteria in the water. It's we take samples and test the water.
Okay, so make sure everything's just running as it should be, based off what we've been told.
Yep, by the government of Ontario.
Perfect. Okay, so what would you say at the what is the water tower's main purpose?
So the water tower's main purpose in the region of Waterloo is to maintain pressure in the distribution system.
Okay.
So we generally fill the water, fill the tower at night when there's no demand, and then when the tower is full, it is good for the day to supply demand, the pressure in the system.
So when you say maintain pressure in the system, how does that? Why do you need pressure in the system?
So when you turn your tap on, if you want to see water coming out with good flow, that's pressure in the system.
Okay.
If, when you get a shower, you're at say a campsite and you have that drip, that's when you have no pressure. So we want to maintain that pressure always the same. So towers are built high in high areas. So we pump them full of water, and then when there's high demand for using water, that high is very high, so the pressure's down, and the water moves out. So that gives you pressure in the system.
The pressure simply helps move the water.
Yeah, exactly. So the height and the weight of the water pushes down, creates pressure in the system, and put it into the pipes of the distribution system to go to your house. Turn that tap on, you have a good flow.
Great. Okay, I can see why our water towers are so important.
Yeah, so they maintain pressure so we don't have to pump all the time and save energy. Yeah. So we don't have to have pumps on all the time, because pumps generally supply pressure as well.
Yeah.
So pumps, and then we don't need the pump, the tower will kick in for extra pressure to maintain.
There we go. Would you say, what are some interesting facts?
So this tower is our highest water tower in the region. It's 50 meters high.
Yeah,
We have 10 water towers in the region of Waterloo, all over Kitchener, Waterloo, Cambridge, Elmira, St. Jacobs. This one is the highest. It holds 7 million liters of water.
Wow.
So that's 23 swimming pools.
23 swimming pools
of water. So that's what
incredible.
kind of gives you an idea how much water's in there.
Wow.
And the water is just at the top.
Yes.
The concrete column is just to hold the water up very high. So
incredible. Thank you very much for your time.
No problem.
Let's talk about water. Water is part of your monthly utility bill. But do you really know what each line means and how together these three systems allow us to deliver clean, safe, and reliable water to you? These systems are connected and play a vital role in creating a safe and healthy city, and have a significant impact on your daily lives. Hard surfaces like rooftops, driveways, and roadways prevent rain and melted snow from making its way into the ground. Our stormwater system collects and transports this water through a series of drains, catch basins, and underground pipes. Stormwater is absorbed into our groundwater or natural creeks and wetlands before making its way into the Grand River. Our drinking water system draws water from these same sources. 80% of our drinking water comes from under the ground. The other 20% is surface water from the Grand River. This water goes through a complex treatment and testing process before it travels through water mains and out of your tap. Once tap water is used for our showers, washing machines, and toilets, it becomes sewage and wastewater. It goes down the drains and travels through a large network of sewer lines and pumping systems to a number of regional treatment plants, where it is carefully treated before being released to the Grand River. Investments and maintenance in our water infrastructure today help to keep our water safe, groundwater and surface water resources secure, and protect our properties from flooding. Our stormwater and sanitary sewers experience fewer breaks and backups, and we see lower operating and maintenance costs over time. Most importantly, we get to enjoy clean, reliable water for drinking, cooking, and playing. Now you know, stormwater, sewer, and drinking water systems working together to keep our city working.
Hi, I'm Kyle, and I'm an environmental scientist, and I'm here today to talk to you about why we sample water. So we're going to talk about 4 different types of water today. We're going to talk about tap water, we're going to talk about groundwater, and we're going to talk about wastewater, and we're going to talk about stormwater. So first we're going to talk about stormwater, and behind me today is a stormwater pond. And this stormwater pond is used to partially treat pollutants that come off our roads and parking lots, like salt and bacteria and even dirt. So some of the sampling that we do with stormwater ponds is to make sure that the pond is working as designed or as engineered. And we take samples on usually big long boulders in bottles, and take samples usually as the water's coming in and as the water's going out of the pond to make sure that the pond's working properly. So the one thing with stormwater ponds that you must remember is that even though they look like ponds that might be fun for skating or for swimming, they're not. They can actually be very dangerous, so you need to make sure that you stay away from them. And there's usually signs like this posted to tell you to keep off.
Hi, now we're going to talk about groundwater and why we sample groundwater. First, we're going to talk a little bit about how we sample groundwater. So inside these blue metal pipes are monitoring wells, so they're groundwater wells, and these wells go deep into the ground beneath us, and groundwater is of course the water that's underneath us in the soil and rocks. So how deep do these wells go? Well, some of these wells can be as deep as a telephone pole is high, and some can even be as deep as the water tower is high. So why do we sample groundwater? We sample groundwater to find out if it's contaminated or if it has any pollutants in it from different activities like gas stations or road salt or other industrial activities like that. And how do we sample it? Well, we sample it with a couple different things. We sometimes sample with pumps, and sometimes we sample it with a special piece of equipment called a baler, which is almost like a long, narrow bucket. And other times we use something called a foot valve, which is what I have in my hand. And it's just got like a little ball there, and we attach a big long hose to it, and then we can move it, and the water goes in through the valve and pushes up through the tube to the surface, but it doesn't go back out because the little ball stops.
Okay, now we're going to talk about tap water. So tap water, whether it comes from a municipal drinking water system or whether it comes from your own private well, is the water that we drink. So it's very important that we make sure that we sample drinking water to make sure it's safe to drink. Now to do that, the municipality, if your water comes from a municipal system, they sample your water daily, and sometimes multiple times a day, and they do that before it comes to your tap. But if you have a private well, so if you live in the country or if it's at your cottage, and you have a private well, then it's the homeowner's responsibility to sample that water. And to do that, you use these sample bottles right here that come from the public health unit, and you take that lid off right there, and you fill it up from your tap. Alright, we have a little exercise here to demonstrate to you why it's important to sample tap water, whether that's private water, private well water, or municipal water. So this glass full of blue beads represents our glass of water, and when a sample, like the sample bottle on the back, is taken to a laboratory and tested, what they do is they take part of that water and they run it through some laboratory instruments to test for the presence of different contaminants. And one of the contaminants that they do look for is bacteria, specifically E. coli. And now E. coli can be found in lots of different places in the environment, including our food, and it can make us sick. So it's very important to make sure there's no E. coli in the water that we drink. So for this exercise, what we're going to do is we're going to take a look at this glass of water, and it's got blue beads in it, and we'll take a little bit of a sample from it, and we will look to see if there's any red beads, which represent the E. coli. Now this glass of water, in this part of the sample, does not appear to have any red beads, so therefore this water would be safe to drink. Now here's a different glass of water, also with the blue beads, and it looks the same as the last one, so it looks like it's probably safe to drink, right? Well, not necessarily. This is why it's important that we sample, because we can't see bacteria, we can't see E. coli with our eye. So although this glass looks like it's okay, when we do our sample, our test sample again, and right there, we find a red bead. We find some E. coli. So that just is to demonstrate to you that it's important, and there's another one right there in the glass, that it's important for us to always get our drinking water tested, whether or not it's municipal, and in that case the municipality does that for you, or whether it's your private well at your home or your cottage. It's always important to get it tested, and you can do that if it's a private well through the health unit and a sample bottle just like that.
All right, now we're going to talk about wastewater sampling. So what is wastewater? First of all, wastewater or sewage is the water that comes
from your sink or from your toilet, and it goes down into pipes under the ground and ends up at the wastewater treatment plant. And this is a wastewater treatment plant in Elora in the township of Center Wellington, and Grace is an operator at this plant, and she is going to show us how she samples every day. So this first video is Grace taking a sample of the wastewater as it comes into the plant. Now we're taking a look at the bubbles in the aeration tank, and wastewater plants have lots of different pieces of equipment to clean the water, and this is one of them. Grace is now grabbing a sample with the sludge judge from another piece of the treatment process called the secondary clarifier, and she uses this to get down to the bottom to get a sample at the very bottom of the clarifier, and then she transfers that into the bucket. And they use this to test the treatment process. And the secondary clarifier gives the solids in the water a chance to settle out before it goes to a polishing step, which is called the sand filters. And now we're going to watch Grace take a final effluent sample after the sand filters. So there it is right there. And you can see how clean and clear that water is. Grace is now in the laboratory. And Grace is looking into the microscope to look at the microorganisms that live in the aeration tank. And these microorganisms help treat ammonia, which is poisonous to aquatic life. And finally, we have a picture of the first sample that Grace took when the wastewater first came into the plant. And that's on the right-hand side. And a picture of the final effluent after it's been treated and just before it gets discharged into the Grand River when it leaves the plant. And you can see the difference between the two samples. That's why it's so important to ensure that all of the solids and toxins are removed from the water before we discharge it to the river.
All right, thank you everybody for listening. I hope you learned lots about sampling water, and I hope you have a great time today at the Waterloo Wellington Children's Groundwater Festival. Thank you very much. Have a great day.
It takes a lot of work to clean and move the water we drink. Harmeet is going to talk to us about energy and water use. Over to you, Harmeet.
Hello, everybody. So in this presentation, we will be going over water and energy use. So before we discuss energy and water conservation, it is important that we have a good understanding of what provides us with our energy and water and how we use them. When talking about energy in our home, mainly we use it to heat and cool our houses, as well as to power our appliances such as our fridges and microwaves. When talking about where we get our energy, in Ontario, mainly our electricity is produced through nuclear energy. Nuclear energy is produced using a nuclear reactor, and within it, within the reactor, we split very, very small particles called uranium atoms, which create heat. This heat then converts water into steam, and the steam turns a turbine that spins a magnet, which creates electricity. Some other ways in which our energy is created in Ontario is through wind energy, solar energy, as well as through water power. When talking about water and where we get it from, in the Waterloo region, 80% of us, and within the Wellington region, 100% of us receive our water from groundwater. And within our homes, we use this water within our toilets, our showers and baths, for our laundry and our laundry machines, and for food. Now let's talk about energy conservation. So conserving energy, firstly, it's a great way of reducing our greenhouse gas emissions, and it also helps lower our energy bill and the amount of money that we use to pay for our energy. So within our house, there are many different appliances which we use, which use energy, and there are many ways in which they overly use energy and ways in which we can reduce them. So I'm going to talk over some main ones now. So firstly, we have our central air conditioner. The hottest times of the year, our central air conditioner can account for up to 1/3 of Ontario's electricity demand. And to avoid using excessive energy from your central air conditioner, you can keep your doors and windows closed when it's on, keep your blinds and curtains closed during hot days, and use a ceiling fan. Our fridges and freezers, especially the older ones, can cost over $10 a month in electricity to use. To lower these costs, keep the temperature in your fridge between 2 and 5 degrees Celsius. The temperature of your freezer should be about negative 18 degrees Celsius. Also, don't overload your fridge or freezer. These appliances work best when they're filled properly. Our clothes dryer. So electric clothes dryers use 3 times more energy than your washing machine. To avoid using a clothes dryer, you may dry your clothes on an outdoor clothesline during warmer months and dry full loads. Make sure the loads which you are drying are full, but don't overload your dryer. Don't fill it excessively. For a pool and hot tub, the pool and hot tub pumps are among the highest energy consumers in our homes, if we have one. To lower their energy, make sure to cover your pool when it's not being used. And finally, make sure you install LED lights. LED lights can save 80% or more compared to incandescent lights, and they last 3 times as long. Quickly, I'm going to speak about phantom power. So phantom power is simply power that is being used by a device when it is not actually being used by the owner. For example, energy being used by lights when we are not in that room. And this phantom power actually accounts for 10% of our home's energy use. To avoid doing so, make sure that you are shutting off your devices such as your televisions, your phone chargers, your computers, your lights when they're not in use. When speaking about reducing your natural gas usage, you should do the following. Lower your home's temperature by 2 or 3 degrees. Set your thermostat to 20 degrees when you're awake and 17 degrees when you're sleeping or not at home. Clean or change your furnace filter regularly. Keep air vents and baseboards dust-free and unobstructed. Let the sun heat your home. Keep blinds and curtains open on sunny days. Make sure your walls are well insulated. Install energy-efficient windows to reduce heat loss. Take shorter showers. Set your water heater's thermostat to 50 degrees and wash your clothes in cold water. In terms of conserving water, make sure to turn off the tap when you brush. Check for drips and leaks from your toilets and taps. And use your dishwasher instead of washing the dishes.
We are really fortunate to have clean drinking water. Not everyone is this fortunate. So let's find out about how other countries deal with the lack of clean drinking water.
Have you ever thought about how water affects your life? Water is crucial to us, but not everyone has access to clean, safe, running water. Now, I would like to take you on a journey to visit Aguascalientes, a city located in the arid region of central Mexico. The area was famous for its hot springs. That is how it got its name, which means hot waters in English. The dry climate and the overuse have changed that. Unlike Ontario, Aguascalientes only has 2 seasons, dry and wet season. All the rain is concentrated in a few months from May to August. The difference is obvious when you look at the vegetation. Plants and animals here have adapted to live in very dry conditions. Plants have deep roots to get as much water as they can. This is one of my favorite plants. It is called huizache. It has tiny leaves that help to prevent evapotranspiration and big thorns so local herbivores don't eat their leaves. Having deep roots is not always enough. Other local plants, like yuccas, cacti, and other succulents, have wax covering their leaves to prevent water loss and are capable of storing water inside their tissues. Humans can't save water inside their bodies like plants. During dry season, local rivers and streams don't have running water. There are water dams in the city that help store some of that water. Most of the water used in Aguascalientes homes is groundwater and comes from deep wells. There are big tanks and water towers that store treated water across the city. But it is not enough. All houses have water tanks in their roofs or cisterns to help them collect water. We visited a local school to talk with some students about water. This is Francisco, and he is in 5th grade. I asked if he has ever run out of water at home and for how long. He explained that sometimes his family has gone a full week without water and he has to go to his grandma's house to shower. He shares some of the ways in which his family makes sure that they are saving water. He said that when they do the dishes, they save that water and use it to flush the toilets. This is Iker, and he's in grade 4. He explained how, when they don't have water at home, he has to go fill buckets and use small containers to clean, do the dishes, and mop the floors. He told me that when he opens the tap at home, it only tickles a little bit, so he can't shower. His mom brings a bucket to the shower, and because they can't wait for the water to warm up, he uses cold water and small containers. The situation in Ontario is very different. Let's take a look together. The animals, plants, and other living organisms are adapted to go through 4 seasons each year. Spring, when the snow melts, temperature rises, and flowers like trilliums bloom. Hot and dry summers, followed by fall, when leaves change color and then fall. And then winter, with cold temperatures and snow. In Ontario, you can see water in different forms all year round. We asked some Ontario kids about water. Let's hear what they have to say.
What do you use water for?
Drinking. I use water by drinking it. I use it by going to the washroom. I use it by washing dishes. I use it to brush my teeth. I use it to get my hair wet. I use it to shower and bathe.
How long have you gone without water?
I've probably gone like 3 or 4 hours without water while I've been awake.
2 hours.
How much water do you think you use every day?
1 liter.
6, but if I have a shower, 8.
What are ways that you can say that you try to conserve water?
Making sure my sister doesn't turn it on to brush her teeth and then leave it there, which she does a lot. I don't leave the tap on while brushing my teeth.
If you're done drinking water and you don't finish it, you could put it back in the container so you can save it instead of dumping it down the drain.
Can you think of other ways to save water? Remember, water is a precious resource. In Ontario, we are lucky to be surrounded by water. There's lakes, rivers, and streams all around us. Most of us here can open the tap and get clean, safe running water. Not everyone is that lucky. Let's do our part and take care of our water.
As our community grows, we need to make sure we always have a good supply of clean water. Now, Peter and Kayana explain how planning and actions each of us can take are important steps.
Hello, my name is Kai and this is my dad, Pete. Here in Waterloo and Wellington, we rely mostly on groundwater for our drinking water.
Making sure we have a good supply of clean drinking water is an important consideration for any city or town. This responsibility falls to municipal governments.
As our towns and cities grow with more people and buildings, I would imagine that we also need to have a plan for making sure there is enough clean water for future generations.
Now, there are 2 primary ways we look at taking care of water. Quantity, we want to make sure we have enough water for everyone in our community. And quality, we want to make sure the water is clean so that we can drink it.
we can help take care of the quantity of our water through conservation programs, better technology, and changing our attitudes about water. What can you do to use less water?
Now let's talk about quality. Governments use maps to show where important aquifer recharge areas are, and also to determine the direction and flow of groundwater. Why is this important? Knowing the time it takes for groundwater to flow underground and reach a well is important, as well as understanding the types of land uses in these capture zones.
These maps help us identify important areas around regional wells. These locations are called wetland protection areas. The colored areas around the map tell us how long it takes for the groundwater to reach the well. The land immediately surrounding the well is the most sensitive and therefore has the most policies protecting it.
On that note, an important way to identify and plan for a variety of future land uses is through municipal official plans. This document here. Official plans and source protection plans set policies that protect important groundwater sources.
This is so important to know because with our growing population, water may be harder to take care of in the future. This year, we have about 1 million people in the Waterloo region, Wellington County, and City of Guelph relying on groundwater sources. Each person uses about 259 liters of water per day, accounting for the food we eat and the transportation we use. That's a lot of water, and that amount isn't sustainable for the future.
Another way that we manage water resources is through reviewing new development applications and implementing land use planning tools. Regional and city land use planners can require that property owners demonstrate that their site is clean or that potential risks have been addressed.
For further reading, you can do research on records of site condition, which is a provincial approval process that occurs when a less sensitive use for land, such as industrial use, transitions to a more sensitive use, such as residential or park use.
In recent years in Kitchener and Waterloo, we know that lots of new buildings are being constructed in close proximity to Ion LRT. Many of these new buildings have had to obtain a record of site condition prior to construction and planning approvals. This land use planning tool is one way that helps ensure that groundwater sources are protected and that any potential risks to the quality of water are being mitigated.
If we conserve our groundwater and manage our groundwater sources well, we can continue to manage our water for all future generations.
We have certainly learned a lot today, haven't we? Well, thank you. Thank you for joining us on our final day of the Waterloo Wellington Children's Groundwater Festival. And a reminder, today's event was recorded, and a link will be emailed to all registered attendees. Now, we're going to end our time together with a song from Sean. But first, I want to tell you about a Kahoot quiz you can play that covers what we've learned today. Details are included in the chat, so make sure you try it out. And now for that song on what to do when it's raining. Bye for now, folks.
Well, the weatherman said you better stay in bed. It's another gray, rainy day. Everyone to spare, there's water in the air. It's gonna wash your smiles away. All the plans you made will have to be delayed because of this H2O. Everyone hide, you have to stay inside. There's nowhere you can go. 'Cause it's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something boring. Well, the stuff we need to live is falling from the sky. No time to celebrate, hang your heads and cry. Farmers might say that showers are a blessing, but we've been told that rain should be depressing. So shut down all the playgrounds, close the summer camps. Imagine what would happen if the children got damp. Hide out in your houses, hide out in your cars. If you want to find some water, go look for it on Mars. Cause parents all know, and you should not forget, the worst thing that may happen is if something gets wet. It's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something boring. Well, the weatherman said you better stay in bed. It's raining, it's pouring, puddles are forming. It's raining, it's pouring,